Now, if the state j is recurrent, then this Tjj, right, is a legitimate random variable, right, the time interval between two returning to time to return to j starting at j. Now that you read j here again, you can look at this random variable, and this random variable, let me call this Tjj2, is also a random variable, is clearly independent of Tjj1, right, because given that you read j, what you are going to at this point, given that you read j, the previous recurrence time of j is not going to affect the future states, the future evolution of the Markov chain. This is by the Markov property, right. So, clearly the random variable Tjj2 is independent of the random variable Tjj1. Furthermore, these random variables Tjj1 and Tjj2 are identically distributed. That is because the Markov chain is homogeneous in time, right. Now, if you are in a state j at any time, it does not matter whether the time index is 50 or 5000, right. Your future evolution and subsequently returning to state j again does not depend on the at least the distribution of the time to recurrence time of state j does not depend on how many times you have been to j before, right. So, bottom line is that this if you look at this Tjj1, Tjj2, Tjj3, etc., Tjj1, Tjj2 dot, these form a sequence of IID random variables if state j is recurrent. Okay. So, what this in turn what this means is that you can argue that given x naught equals j, recurrence times of state j can be viewed as renewal epochs. So, what we are saying is that, so at time 0 you started at j, then you return to j here, and then you return to j here, and you return to j here, and so on. We just showed that these guys are all IID, right. So, these are all renewal epochs. So, the times at which the j occurs again are renewal epochs, and these intervals are all renewal intervals, they are IID, all right. So, this will be a very useful tool, because we know a lot about renewal processes already, if you remember from our previous study, and we can use results from renewal theory, renewal reward theory, and so on to derive some very important and interesting results about these countably infinite state Markov chains. Now, let us get back to considering this Fijn, all right. So, this Fijn, if you remember, is just sum over Fijm m is equal to 1 to n, right. So, this is I can pull out Pij, which is for m is equal to 1, and then write some m is equal to 2 to n Fij of m, and Fij of m I already know an iteration, right, from earlier. So, I can write this as Pij plus sum over m is equal to 2 to n sum over k not equals j f Pik f kj of m minus 1, right, which I can write again as Pij plus sum over k not equals j. So, I am just pulling this summation inside, all right. This is justified because everything is non-negative, right. So, then what do I get? So, if I pull this summation inside, I will get some m is equal to 2 to n of these fkj's, right. With what is that equal to, right? That will be equal to, so Pik comes out and the summation goes in, I will get big F k j of m n minus 1, all right, and this is for n greater than 1, okay. And of course, what is Fij of 1 is simply equal to Pij, okay. So, this is the iteration for big Fij of n. I have this is the iteration, okay. Now, what happens if I take n to infinity? I should have the equation Fij, see all these limit exists, right, because they are all monotonic in n. So, Fij infinity is equal to Pij plus limit n tending to infinity sum over k not equal to j Pik Fkj of n minus 1. Now, I am going to push this limit inside the sum, okay. This requires a justification. This is because remember now that you are sending a limit inside an infinite sum, okay, and this does not always hold, it holds in this case, okay. The justification for this will come from the fact that the terms are non-negative and this is bounded above, all right. So, you can invoke some bounded convergence theorem or something like that and push the limit in, okay. So, let us not worry too much about that. So, if you push the limit in, you will get sum over k not equals j Pik Fkj of infinity. All right. Fij of infinity is equal to Pij plus sum over k not equal to j Pik Fkj of infinity. Now, this can be viewed for any j as a set of equations over I, all right, and you can solve them. Now, so you can just you can view this as equations on, you can write this as Xij, right, is equal to Pij. I am just pretending that Fij infinity is Xij, all right. I am just calling it some variable sum over k not equals j Pik Xkj, all right, and this is for all states I, right. You can say that Fij infinity, which is the probability that you eventually hit j having started at I, is a solution to this equation, all right. to this equation. Okay. Now, if you put xkj, xij is equal to 1, note xij equals 1 is always a solution to this above equation, all right. Does it mean that Fij infinity is always equal to 1? No, not necessarily, all right. What we can show is that although Xij equals 1 is always a solution to this equation, there may be a solution Xij which is smaller than 1 also. There may be, there does not have to be. Xij equal to 1 is always a solution, but there may also be a smaller solution. Okay. What we can show is that if state j is transient, there is another solution Xij, I belongs to S, which is the true solution to Fij infinity, all right. So, if state j is transient, then you may not there is no guarantee that you will hit j from I, all right, in which case Fij infinity will be less than 1, all right. So, in that case there will be a solution Xij which is strictly less than 1, which is the true solution to Fij infinity, all right. And in fact, the smallest solution of this is the true solution always. Okay. So, it can be shown. So, there is in fact worked out solution, guided proof in Gallagher that says that the smallest solution is the true solution of so let us call this some star is the Fij infinity. Okay. But if state j is recurrent, then there will be only one solution, which is Xij equal to 1, all right. Now, if you look at this, let us particularize this equation for the case when I is equal to j. In particular, if I write Fjj infinity is equal to Pjj plus sum over k not equal to j Pik Fkj infinity. If I look at this equation, now suppose state j is recurrent, i.e. Fjj infinity is equal to 1, all right. Then what happens is that you get 1 is equal to Pjj plus sum over k not equals j Pik F kj of infinity, all right. Now, if state k is such that P I k is strictly greater than 0. Sorry, I should write. I think I made a mistake here. I should be P j k. I think this is P j k. I'm sorry, right? So P j k is strictly greater than 0. That is, state j is recurrent, all right, and there is some other state k such that I can go from j to k with positive probability. Then if you look at this equation, okay, this equation will imply that since the left hand side is equal to 1, all right, this is only possible that if Pkj is strictly positive, then Fkj of infinity will have to be 1 for all k such that Pijk is strictly positive. Okay. What we have essentially shown is that if state j is recurrent, if this guy is recurrent, right, if this is a recurrent state, and if it is possible to go from j to k, Pjk is strictly positive, then with probability 1 you are going to eventually come back to j. Okay. Fkj infinity is 1. So, starting at k, you are assured with probability 1 that you will return to j, all right. In fact, you can extend this logic further. This is only a state k which is one hop away from j, from a recurrent state j. In fact, you can extend this logic and prove that if j is recurrent and I is any state such that j arrow I, meaning that I am able to, there is a path of positive probability from j to I, okay, then f I j infinity is equal to 1. Okay. So, what we have above, what we have argued above is that if k is if Pjk is strictly positive, meaning that there is a one hop path from j to k, then return from k to j is assured. This lemma is generalizing that, it is just an iterative. You can show that if there is a two hop way to get from j to I, or a 3 hop way to get from j to I, you can just inductively show that return from I to j, eventual return is guaranteed with probability 1. Okay, this is just an inductive proof using the logic above. All right, you can do the proof yourself inductively. So, this is great, right. So, if I am considering a recurrent state, okay, so the recurrence is given a particular meaning now. If I am at a recurrent state, and if there is a state that I can get to from j, all right, then I am assured that I will return to j from that state. Okay. So, that ties in with the understanding of recurrence, that if I start at j, I should return to j with probability 1, right. So, any state I get to, I should be able to get back to j with probability 1, right. That is what this lemma is saying. There is another lemma which you can prove, which is sort of the opposite of what the above lemma says. If j is recurrent, and I is any state such that j arrow I, then f j I infinity is also equal to 1. Okay. So, the situation is the same, j is recurrent, okay, and I is some other state which I can get to. Let us say I can just get to in 1 hop or 2 hop or whatever, right. Then what we are saying here is f j I infinity is equal to 1. So, if I start at j, I am assured to hit I with probability 1 at some point finite time. Okay. again the proof of this is from using the fact that your guaranteed returns j is recurrent. So, you are assured to return to j, right. Whenever you are at j, you are assured to return to j, right, and these times to subsequent returns are all random variables, right. So, during one of these returns there is a positive probability that you will eventually get to I, that is the logic of the proof. Okay. There is a positive probability alpha that any time you get to j, you may go from j to k, k to l and l to I, let us say that is the positive path probability. The probability that, let us say this probability is alpha, this probability is alpha of going from j to l and l to I or something like that, right. The probability that you keep coming back to j, but you never take this path actually will go down geometrically fast, okay. That you can argue some more rigorously, okay. This is in fact done in exercise 6.5 in Gallagher. I will not spend class time on this, but the logic is fairly straightforward, okay. So, we have said two things. If this is the picture, if j is recurrent and I is a state which you can reach from j, if j arrow I, then Fij infinity is equal to 1 and Fji infinity is also equal to 1, okay. What that means is that any state which you can get to from a recurrent state, you are guaranteed to come back to j, that is what the first lemma says. The second lemma says whenever you are in j, right, you are eventually guaranteed to go to that state I, okay. This is very nice because we can prove another lemma, okay. Consider so a situation where state j is and j arrow I. So, state I is accessible from state j, okay. Then we can prove that, so you can prove this is a lemma, then state I is recurrent also, okay. So, as long as j arrow I, state j is recurrent and j arrow I, then I am guaranteed that I is also recurrent. Why is this the case? So, you are looking at j which is recurrent and you are looking at this I, all right. I want to look at I want to look at Fii infinity equal to what, right. If Fii infinity is equal to 1, I am done, right. Now, you consider Fii of m plus n, all right. Fii of m plus n is surely greater than or equal to Fij of m times Fji of n for all mn greater than or equal to 1. Why is this the case? So, Fii m plus n is nothing but the probability that I start at I and come back to I at some point between 1 and m plus n, correct. One way of doing this is to go from I to j in m steps, right, within some time between 1 and m, and then between sometime between m and m plus n, m plus 1 and m plus n, come back go from j to I, right. So, this equation follows. Now, I can just take limit. So, you take limit I get basically limit m and n tending to infinity, Fii infinity is greater than or equal to limit m tending to infinity Fij of m times limit n tending to infinity if j I of n, okay. And I know that from the previous lemmas I know that both these limits are equal to 1. So, this is equal to 1 times 1 from the previous lemmas. So, f I of infinity is greater than or equal to 1, which means that f I of infinity will be equal to 1, alright, being a probability, which means that I is recurrent. So, which is very nice. So, we have proven that theorem, we have proven the following theorem. If state j of a countable state DTMC is recurrent, then every state accessible from J is also recurrent. All right. This means that in particular all states in the same class of J, same class as J are recurrent. So, if you have a state J, any other state you can get to from J is also recurrent, all right. So, we are getting back the old result that we know for finite state Markov chains, that all states in the class must be of the same type, which must be either all recurrent or all transient, all right. So, this theorem statement is true. Actually, I do not even have to say countable state, right. I can just say this does not, I do not have to explicitly say this, right. For finite state also this is true, we know this to be true, right, except the definition of recurrence is was different over there, but we can show that the current definition holds there in the finite state case also. So, this is a very nice result, right. So, in each state in a class must be, all classes in a state must be all recurrent or transient, okay. We can stop here.